Good morning, everyone. Thanks for joining this third day of the GPU programming with the HIP course. I will share the schedule for today. So the idea of today is to review review previous day on the solution of previous exercises. Okay, review of last day. We have seen I was checking, yeah, last day was mainly about memory, like how in the first day we saw that the memory, the host and the device, they have different memories. So to use the device, GPU, or to call it, yeah, call it a device, we need to copy the memory from the host to the device and use the memory. On the day two, we have seen that we, rather than do it in an explicit way, we can tell the runtime that allocate the memory, and the runtime will be in charge of copying the necessary bit of memory from host to device, or the way around. On what, okay, that might be easier, but the issue that I see is that because we don't control when we copy the memory, and this could lead to some performance issues. So personally, I prefer to do it manually, to say, okay, now I will copy this, now I will copy that, and play with that. In the afternoon, we saw two other types of memory. That was shared memory, that the shared memory is inside a block, and it's like a smaller than the I don't know, yeah, the main memory that is used in well, I think it's called, yeah, global memory of the device. And also we have a small area for constant memory, that this is used for constants, as the name said. And last we saw streams, that by default we use only one stream to execute memory copies, kernels, etc. But we can have more than one stream. To, for instance, if we want to do a memory copy, we can do it in parallel. If we need to copy two vectors, we can create two streams, one per vector, and perform the copy. I think this was explained the first day, but what would be good, maybe a reminder. Now there are like new technologies that rather than having different memories, let's say the host has one memory and the device has another memory, we'll have a like unified memory. So the memory will be kind of the same for the host and the device. I think for AMDs, the AMD MI300, and NVIDIA also implements with the Grace Hopper. I think it's Grace. Is like, yeah, now there are a lot of progress and advantages with this. I will have a look, and later, because I see that there are some questions on the Etherpad about that memory. I will answer them and provide more information. Okay, so well, this is like also I forgot to ask if you have any questions. Please feel free to write them in the chat or unmute yourself. Okay, so next we can see how to solve, because we have a few exercises from last day. We can see how to solve we have actually three exercises for shared memory. I think I should have a load there. Is this yeah. So yeah, this was day 2. So we have three exercises. We have for shared memory, we have one for constant memory, and also we have for streams. Any preference, or shall we start with the shared memory? Okay, so let's. I will share my screen. Okay, so yeah, before starting, I was checking that we have the GPU nodes. We have the 4 of them to use, so that's good. We can check that with the S-info. And yeah, I also moved to the from home to work. So you see that in my prompt, I'm in the work directory. So if I do ls, yeah, we'll go to the Archer 2 GPU cores, the section 2.05, and I see that they have okay, what yeah, I was playing with the reducer just to start from scratch. Check out okay. So VI what is this? Yeah, this is the name. Actually, let me. I don't know if it's in the. Yeah, let me see the exercise there. Actually, we'll copy this here in the. Yeah, so the exercise here is we have this kernel. I will, no problem. It's yeah, I see that yeah, more people join. We just have like a brief summary of second day, and now we will solve the exercise of the shared memory section. That is, I will share it here. So what we'll do is we have this kernel, and actually we can execute it and see if that works. So we have to compile it is we'll need to see the heap. So yeah, to compile that we will need to use this raw path exercise d.heap. Is this the exercise that we want to? And let's patch submit. It's taking some time, but okay. There. So now I can do sq minus me. yeah, since that this is already done, so you can see the I think the issue is I didn't load the right set of modules that if we go to the Archer 2 documentation, sorry, the course documentation, I need to load this this paste. Let's see if I know it works. Actually, we'll see. Yeah, this has been generated, so submit. I mean, it could be also something on the of the template that is not maybe not working, but well, we'll have a look at that. I think there is a excuse me. Oh, it's already. Let's see this one. Keep error over. Maybe something weird of the template. Okay, well, we'll. Yeah, I don't know. I don't understand the yeah, that we have the solution. Okay, what we can do to see. Sorry about that. We can copy the solution, compile the solution with this command. Now dispatch, and now see if that works. Okay, it's in the queue. PD is pending. So we'll execute that again. Okay, this have execute, and the number is this one. Could be that maybe we need that in the or maybe there is something. I don't know. Binary for GPU. Did you get also the same error? I'm not sure if I'm doing something wrong. I don't. Okay. Let me check because I have some exercises that they used to work. I don't know if it's a question of the exercise of the. I think this one works if I. Yeah, let's execute this one. Or maybe could be. I will comment this. Okay, let's. The number is this one, so it must be this one. Sorry, I don't know what is happening here. Running. So this is the last run. This is the review share. Could be something of the. I don't know. One moment. Actually, no. Section 2.2. Okay, I think I use a different because I see this command is longer than not the one that they used before. Maybe it's that. So I submit that. I execute minus me. So we submit 77, 77. Okay. Sorry about that. The issue here was to yeah, we need to update that in the I was using this is the right command to compile. It's a bit of a nightmare because you need to specify yeah, a lot of options. And what I was doing before, I was compiling the code, but I think was compiling only for CPU, was not compiling for the GPU device. So if we see that, we get the error that is a heap error, no binary for GPU. It means that yeah, the code has been compiled for the CPU, but not for the GPU. Okay, so now that we have that, we see the exercise, git checkout. This is to revert the changes of the exercise. And now we see if, what we get. Oops, okay, I wanted to. So yeah, this is the kernel that we want to modify. And in theory, now if we can compile with make and start submit. Okay, so we let's if we okay, so we see that yeah, we get that is correct, so it works. So what we will do is we will go actually we'll see if I can copy this. Yes, possible to copy. So what I will do a copy of the kernel and I will call it the dot parallel. So here the thread ID is the thread ID of let's say the global, but because we will share shared memory, that the shared memory is inside the block, we will also use this value that will be thread ID dot x. So okay, so what I will do is this sum I will create a share memory, a vector that will be because yeah, will be double. Well, this will be a temporary, and the size will be the threads per block that I think are set here. Yeah, we have a define a well, yeah, constant that this threads per block. It's not a constant. It has another name. I forgot the name. That is, I mean, what the thing is when you compile the code, every time that this word appears, will be changed by 256. So it's a common way to, so it's a threads per block. Okay, so we have this variable here. And now, let me see. We need to do this operation here, but this will be done in by each thread of the So xi is 0. The thing is, I need to figure out what the I will be, because we are threads per block, and we get x, y, the result. This will be SMP, that will be thread per block. Well, the index will be thread dx.x, and here will be x multiplied by this. So I think here will be something like this. You understand this first step? We have a temporary vector that is in shared memory, and here we will store this operation here. What is the next step? Synchronize, because this could be done in the different times, but once that we have this vector complete, in shared memory, what we want to do is to sum all of the elements and save them into the result variable. So for that, once that we do this operation, I need to synchronize the threads. And this is like a double underscore sync threads. Okay. And now, rather than if here, because if we keep this will be the same for the whole, the same for the whole program, but we want to use a thread ID. IDX, no. If is equals 0, this keeps the same. Actually, this keeps with this will be threads per block. And sum will be tnx I. And here notice that this could be, here we could have a problem, because if we have more than one block, this condition will be true more than once. So here what we need to do is to do an atomic addition. That is a result sum. Rather than this. I think this is okay. I'm not sure if I'm forgetting. Well, here is important, in order to avoid problems here, this will be good to add if TID is less than n. Otherwise, we could have problems here when accessing this. And actually, because we are doing that, that would be useful to initialize as well. I mean, we can either do this or do else initialize this position in memory. Let's try and see if that works. Okay, let me check main, because if you notice, we have changed the name of the kernel. So here we have ddout now will be parallel. And we are using blocks. The number of blocks, thread per block. Let me check the size of the vector. Okay, it's quite big, so we have several. Well, okay, let's see if that. Now, if we compile, we make. I get an error here that I forgot the semicolon. VI exercise. Exactly, yeah. Oof, okay, compiles, let's submit. And let's see how it goes. Learn 9 to be like these numbers. I'm okay. It seems that it works. Any questions regarding this exercise? I will show you the solution in case that. Is it clear? Which one do you want to solve next? Do you want to see the solution of the constant memory, or okay, I see that question in the chat, if there is a way to determine the amount of shared memory available rather than looking the GPU specs. I think there is a I need to check. There is a command that gives you the information of the GPU, but I will need to check. I will have a look and let you know. Any other questions? If not, which one do you prefer to see? Well, we can see the. Okay, well, let's go. Let's see if we have time to see all the. This doesn't have the make file as well, so I will. Well, actually, there is a way. Yeah, I need to. Okay, exercise. I think this is a bit more complex, this exercise here. My kernel. I will check if the exercise works. I will copy the make file from the other folder. And well, let me check if pending. Okay. Okay, since that it works, but because we have actually, yeah, we are using a kernel, but actually the kernel is serialized. So let me see the exercise here. Actually, let me check how the kernel is launched. Kernel is blocks, threads per block. Okay. And here we have a okay, but we see that here we're using like 1D. Let me have a look at the course exercise. Actually, I will share with you the. And you see the. So, well, we have this matrix vector operation. The kernel is already doing that. So it's a new template with a serial version, blah, blah, blah. We have one block per row. that is the number of the columns is equal to the number of the threads per block. Okay, so what we want. Okay, this is like normally when you code something, you need to go step by step. And the thing is, they tell you first parallelize using one block per this the assumption of one block per row, and once that we do that, we can do it in the into the. Let's see if that. So the first attempt will be. Let me check the exercise. Oh, okay. I need to switch the window. So sum of sum. Yeah, actually it's pretty similar of the to the previous one. Um, yeah, here will be to define the. But the thing is, okay, we have I and J. Was wondering, do you want to see the solution to this exercise, or you want to? Well, we can have a look later at the with the streams, or you prefer to see the solution of the other? Well, let's try if we have time to see the solution to this one. So here again, I need to create a shared variable with the how this. And here I have the trick here is that I have a double. I have a double loop. So what we want to okay, let me check the answer of the. Yeah, here what we want to, okay, we want to eliminate the two loops here. So we will need to calculate the correct I and the correct J. We see, because I see that if we want to solve the other exercise, maybe we don't have enough time to go. So, but let's write this. If we see the solution, we have the solution of this exercise here. You can see that yeah, we will not have like enough time to. So you see that this is the original kernel that we have. That we have here the two loops, one with the for the rows, and J will be for columns. And here, if we see the solution, it's pretty similar of the previous step. If you remember in the previous one, you do the operations here in shared memory. Once that you do that, you call a synchronize the threads, and then the thread 0 in each block in each row will accumulate the contribution. You remember it's pretty similar of the previous one. The difference is here is that you have because we have in 2D, we have I will be the block dim x for the x the x x axis, yeah, we have E, and J will be for the y axis. And then this is actually we use that, but well, we can use thread ID. So this will be if we parallelize it like just the yeah, row wise, because each each thread will do a different row. No, this is this is already parallelized in 2D. Yeah, this exercise is a little bit more complex to see, but not sure if you have any questions or. If not, we can move on to the other exercise, the one that we need to create 2 streams. Is that okay? I don't see anything in the chat, so hopefully all is okay. I'm not sure if there are questions, if you are following this or. Okay, thanks. So yeah, I just wanted to so section 401. Also, I see here that we don't have a solution, but we will. I will upload that. Right. So the streams exercise, that is, we have this implementation, and what we will do is okay, this is a type of, so actually what we'll do is we will what we have done before. We will copy, well, let's copy the make file. In theory, the exercise should work, because what we will do is just doing the, here I will need to go to the actually, I will try one thing and see if that works. I will share my whole screen. And I will do this window here. I don't know if there are a way to do this now. No. Let's do it manual. Or the exercise said the following is for vectors x and y, replace heap main copy with an asynchronous operation using two different streams, and make sure that the data has reached the device before the kernel launch. So if we do vi no submit, well, actually let's check the results here. Yeah, this is because I'm using the profiling and has a lot of, yeah, this is the row that I want. But yeah, since that it works. So if we do the exercise, you see here that I do down two mem copies. So they want us to do it in using streams. So if we go to the document, to the course documentation, we need to declare two streams. So I copy that, I move here, and I will make them here. If streams, I will say stream X and stream Y. And I need to initialize these streams with this. So actually we'll do it here. Stream X. Okay, so now I define these two streams and I initialize them here. And to do the memory copies is same, but it will change. Also, I will make a copy here just to leave you. So this will be heap mem CPI asynchronous, and dx will be the same, source will be the same, size will be the same, kind the same, but here I will need to specify the stream, so it will be stream x because I'm copying x. Yeah, fine. And here same change. Actually, I see that there is a typo here. I should have used, I will change this to follow the, okay, so I have this, what this said that before, remember before launching the kernel, that is here, I will need to synchronize the streams. Otherwise, I will launch the kernel and these copies could be not done. So here what I do is copy, paste, and here I need to say the stream X and stream Y. And hopefully it should work. Snake and submit. Okay, so waiting. I was just thinking, I thought that the break was at 11 and was 10:45. Sorry about that. Wanted to follow the schedule, but I just noticed that. I'm sorry. Oh, it's still since that the GPU is busy right now. So I think it's minus P GPU. Let's see if that. Ah no, there are. Okay, also go. Okay, so yeah, since that the result is correct. There is a part that is showing that in Perfecto, but the thing is, I think we need to copy. You see all of these files. We need to open this one, results.json. Actually, I think I can do it. I think I can download it. Yeah, we'll do here. Oh, I should have chosen the. And I think if I go, it's Perfecto, right? The URL. Ah, no, this would be Perfecto. Yeah. Actually, I can make this bigger. Open freeze file. Sorry. Oh, there's an error in there. Oh, no, it's not. Okay, here, yeah, my screen is not, but if this is a heap stream create. If you open, well, you see that the heap stream create takes a lot of, if I reduce this, takes a lot of time. I'm trying to zoom here. Okay. So yeah, this is a heap string create. Then I have the heap malloc. This heap that's, I don't know, but this is executing the same. Okay, there is some. No. Copy host to device. Okay, shows here, but yeah, shows that the copy is done here and here. I will double check because it doesn't look like yeah, seems that it's using different threads, but doesn't look that they're using different. I will need to double check. Oh, well, you see that with the Perfectus, you can have a look. Okay, I need to double check this better. Any questions? You want to have a break now, or what time is it? We have the we can have a 10-minute break until 11:15, and then we can continue with the graphs, in case that you have any questions. So yeah, let's have a quick. Actually, let's have until yeah 20 past. Okay, we'll write that in the chat, and yeah, see you 20 past. Okay, welcome back. Let's see. I have many windows open. was this? Which one is this one? Let's see if this is the link. Yeah, okay, I can share the. So now I would like to talk about graphs. And first, I would like to start with the heap, the AMD documentation. I will share the link because I would like to show you like some figures in order to understand better what we have seen so far. This what is a stream that you see that in the figure. Not sure if the okay you cannot. Oh well, yeah, you can now see the. You see that, for instance, in this case, if you look at the left-hand side of the figure, you see that we have two streams, stream 1, stream 2, and we have the kernel A, we have a heap device synchronized, we have two kernels running in parallel, we have a heap device synchronized. So here we will have let's see this workflow or this pipeline using streams. We can do something similar using kernels. Kernels is what we have in the kernels is that kernels using graphs. When we create a graph, each node will be either a kernel or a memory operation, and we will have dependencies. So you see here that we have the heap devices synchronized. This is because kernel A must be finished in order to start kernel B and C. And using a graph, this will be the representation. We execute the kernel A, and these are dependencies. Once that the kernel A is done, we can start with the kernel B and C. And this is the same. Kernel D depends on kernel B and C. So this is a way of executing this kernel pipeline of dependency using graphs rather than using streams. Here is also explained that using graphs could be more efficient. If we see this is this will be the time. This like the x-axis will be time, and we will have the host activity is here and the device activity. So we see here that we have several kernel launches. So we have the kernel launch A, B, C, D, and there is like some idle time here. But when using a graph, we have the graph launch, and using the device activity that everything is, let's say, done faster. So you have this part. This is what we call it the speed up. Sorry. So if we move to this to the theory. So this is the idea of so this will be like a stream in case that we don't have let's say we have like a, well, this could be like a one graph or the graph. What I haven't explained. Sorry, my voice is not doing very good. So well, what I explained, we have the nodes could be either memory operations or kernel operations. Well, this is called a directed acyclic graph. So the way of creating a graph is we define the variable with the graph, and we execute a heap graph create. Flags will be well, this is we have here some flags, but there will be 0. So here we initialize the graph, and this will be like the once that the graph is created, we do the work, and then we destroy the graph. So the thing is, we create the one thing is creating the we create the graph, but then we need to add once that the graph is created, we will need to add up the nodes to the graph and the dependencies, etc. Once that we have done that, we will need to execute the graph. So we will need to instantiate the graph and launch the graph. So bear in mind that there are like 2 operations: create the graph, create the nodes, etc. And once that the graph is let's say defined, we will need to execute it with these commands here. And there are more the node types. Here we have like a mem copy, so copies of memory, mem set to set the memory to a value, kernel. Also we can have a CPU function call. This is a bit complex because we will need to define everything by hand. We have for each kernel, for instance, we will have these parameters that we will need to set up to when we create a kernel node. We will need to specify the number of blocks, the number of threads per block, the parameters of the kernel, and the function itself. So you see that we do it in that way. So the parameters, we initialize them to 0. Then the kernel arguments, we save them here in this variable. And here we need the function will be this one, the kernel parameters this one, the blocks and threads per block will be this. So once that we have that, we will need to create define the node and add the kernel node. This will be my graph, the kernel node that I have defined here, and the parameters. And will be similar. We have seen the kernel node will be similar with the main copy node, but the structure contains more. We have the kind. That kind means the direction of the copy. That could be from host to device or device to host. And here we have the pointer of source, pointer of address, position that by default will be 0 could be the offset in case that we have a large vector and we want to make copies of copies of a chunk of that vector rather than the whole vector. We can use this variable position. And extent will be the dimensions. That will be like how much we want to copy. So to translate this function to a node, again, we will need to define the node and use heapmem copy 3D parm. This is the parameters. And here I need to define the kind, that will be copy host to device. And then I will need to use these functions here to define the position, that will be 0, the extent, that will be the size. And because it's a 3D, I ignore the second and third dimension. So I just use one dimension. Well, actually here the user. Okay, this is to create the pointer. The thing is with graphs, this is like a bit more complex. So for instance, here to define the source and the destination, the pointer, we need to use this function and use this pointer, the amount of data that would be similar to this one. And the information is added using remember that before we have used a heap graph add kernel node. Here we are using mem copy node. And also for synchronization, because we use a stream to run the graph, we can use the synchronization using a heap stream synchronize, but also we can use a heap device synchronize. I forgot to mention on the documentation, there is another way. This will be the manual way to create a graph. There is another way that I will share this tab instead. Here, there is a capture graphs from a stream. Actually, here you have the source code. And what it does is you define capture stream. You use here stop capturing the operations assigned to the stream. So you record the operations that are in this stream that is called capture stream. So here you do heap malloc async, defining this stream. Also launch host function. So you do all of the operations, all the normal operations, let's say. And then here you stop capturing this. So you do heap check, heap stream and capture. And then you execute the graph for the, because this has been the capture string has been saved here. And now you execute the graph. Launch the graph. And we verify the results. And also what we have seen, what is on the course documentation, is to do a explicit graph creation. This same create a graph, create the nodes, and dependencies. Also here you have another example how to do this. So the exercise, if you want to play, is the exercise of. I think there is a solution here on the folder. So this using this template, play with the. You can create. Two nodes that each node will be a memory copy, and then you can create another node that is another node that will be the kernel. So you can execute the two memory copies on the kernel using a graph. Oh, well, yeah, you can play. Yeah, you can play with the heap and copy. Yeah. Any questions regarding graphs? If not, let me check the schedule. So we will have again this exercise, time for this exercise until noon today. That we will have the break. At 1 p.m. we will learn how to use more than one GPU, and later we will see the exercise that you can play with that in the afternoon. And yeah, that's it. Plus, so yeah, time for exercises until noon, and then we will have the lunch break. Please, any questions? Let me know in the chat. Actually, I will check because I have seen that there are some questions in the chat. I will provide you with an answer. Okay, I hope that you had a nice lunch break. Let's finish this part of the theory of the course. What we will talk here is about device management, because as you may be aware, when we use Archer 2, a node has more than one GPU. So you can select, for instance, two GPUs, and you can execute one kernel in one GPU, one kernel in another GPU. So you will have like another grade of parallelization. You have the parallelization that you can achieve in one GPU, but also you can use both the GPUs. For instance, if you have several kernels, you can use execute one kernel in one GPU and another kernel in another GPU. And actually, it's pretty simple. Let me show you yeah. There must be this one, yeah. So to check how many CPUs we have available, we will need to use this function, heap get device count. With that, we will get the number of GPUs, number of devices. Remember that the numbering will start with a 0. So in case that you have two GPUs, the first one will be 0, the second one will be 1, and so on. To choose which GPU you will you will use, for instance, to allocate memory, you will need to do first a heap set device and put the corresponding device ID. And when you do that, all the operations that you perform will be done on that device, on that GPU. Here there is a concept that is pure access, that you can do we have seen copy from host to device to host, but there is a copy that can be done from device to device. So imagine that you have here there is let's see if I can put everything here. So if you want to copy, well, you can do either this, to transfer device to device from pointer 1 to pointer 2, but also that you maybe now this is like there is like a similar concept with when we have with the new architectures like Grace Hopper, that GPUs could access memory from another GPUs. Here is using the PCI Express, but for instance, for the Grace Hopper, there is the NVLink that is between the. That is, if you go to Etherpad, there is one of you share share an article that explains a bit more about that. Also, to check if this is enabled or not, because on the AMD, depending on the configuration, could be enabled or not this access. The advantage with the Grace Hopper that is the access is way faster than using. For instance, if we use Archer 2, we have two GPUs, but rather than using also because it's a different vendor, is AMD rather than NVIDIA. Rather than using a direct link that doesn't exist, we need to go through another route, so it would take longer to access. And to check, there will be these functions. Here there is a small exercise that is you can do some testing or some benchmarking to see how long does it take to do access or copy from host to device to host, also device to device. You can play with that with the and measure the bandwidth of it. I see that there are a few questions in the chat. I will okay, there is a question about the performance of device-to-device transfer compared to host-to-device transfer. I was thinking I will need to see I will try to find a picture of the architecture, but I will say I will need to let's see test that, but I will say that device to device will take longer than host to device, because device to device will need to go through host, so will take longer. And then we are talking about Grace Hopper, that this is NVIDIA, but also AMD provides the MI300, that they also have some sort of unified memory. Also, now that we are talking about memory, because was a question on the chat about a paper. Let's see if I can. I would like to share and explain to you what we are. So there was a question in the chat about Grace Hopper. So let's say this is the let's say we have now, we have a CPU here and we have a GPU. We have the CPU physical memory that is here. I imagine, yeah, hopefully you can see the pointer, mouse pointer, and you have the GPU that is here. And you see that there are two, because when you access memory, the CPU, for instance, wants to access memory, so there is a pointer to a table, and so this pointer and this table has a pointer to the right position of, in this case, the CPU physical memory. And for GPU, similar. So you see that there are two page tables, one for the system and one for the GPU. The difference here, when we are talking about Grace Hopper, or also this apply to other architectures of, is that we have the same table. And here, when if the CPU wants to access this region, well, the page A that is in the CPU will get access, and actually that will be, let's say, called local access or CPU resident access, how it's called here in this white paper. But if we access from the GPU, will be also possible. They will be called remote access, but they will need to go through the NVLink. The way of checking that, I'm not sure if you are familiar with the NUMA memory, the non-uniform access. The thing here is that we will not need to do memory transfers between CPU and GPU, because GPU can access CPU memory and CPU can access GPU memory. But you need to bear in mind that if the GPU wants to access page B, will be faster than accessing page A, because page B will be in GPU physical memory. So we will also, like, if you check here is oh, sorry, I thought that you were checking the pointer. If you see here is closer to the GPU, but if they want to access to the CPU, will need to go through the NVLink. There is again, if you are familiar with NUMA memory, there is a technique called first touch or touch zero. I don't know. That means if you do a malloc of, let's say, of A and B, if you initialize to 0 page B using the GPU, the memory will be stored here in the GPU. But if you use the CPU to initialize the memory of A, this will be stored in page A. This is called first touch, I think is, I will write that. So we're talking about the NUMA, and the technique is called first touch, I think. That this is also used when we use OpenMP, and we have, for instance, on Archer 2, we have different NUMA regions. So if we want to a thread that has better access to this to a given NUMA region, that thread should initialize that bit of memory in order to locate that bit of memory in the NUMA region that gets access faster. What is done behind the scenes here is that if for some reason that I think this is done by hardware, and that's why it could be faster. This is a new technology that I need to admit that I'm not fully familiar, or I haven't used that much, so I might be wrong. But imagine that we have a page A, and this is initialized by the CPU, and the page A is in the CPU. The problem here is that the GPU is all the time making access to this page in memory that is on the CPU. So we need to go all the time through the NVLink. Behind the scenes, what the runtime can do is do a migration, do a copy of a page A from a CPU to GPU, and once that the migration is done, the performance will increase. But again, this is done behind the scenes, and this is done, I think this is done at a kind of a hardware level. I will share the paper. The paper is on what is here. Also was a question in there that but bear in mind that also there will be will take some, will not be how to say, a GPU could. This is similar to what we have seen of a peer access, that you can access to the physical memory of another GPU, because here you have a NVLink page table. This will be possible. What I imagine here that accessing this memory. Oh, okay, I need to click in order to access this memory rather than this. It will take longer. Will go through. Actually, I don't know what the link will be between the GPUs, but it would take longer. But yeah, the idea is imagine that all of these memories now in Grace Hopper in new architectures will be NUMA, will be considered as NUMA regions. So yes, you will have access to all of them, but you should bear in mind that it will take longer depending if you are on the CPU or GPU to get access to the memory, depending on where the memory is saved in there. So here is kind of when we use well, they said here is translates CPU malloc to CPU or GPU. When we use malloc, that memory allocation could be saved on CPU or on the GPU. The way of choosing where is to using the technique the first touch. I'm not sure if that clarifies or makes things more difficult. Any questions or any comments? I will try to find. I think that I have some slides with the AMD GPUs and see if that because we have for the AMD that is the MI300 that is also like they have this idea of unified memory. I will try to okay, so I will share this. So here there is a better picture. GPU could access the memory to the CPU 0. GPU 0 could access memory to the GPU 1, but yeah, they will, here in this graph will be a PCI Express. I don't know. I can double check how it will work with the NVIDIA GPUs or AMD GPUs. All right, here we have an exercise for to play with the memory transfers. Also, I would like to share with you there is a similar course. This is for HEAP, but if you want to check the content of CUDA, this course is if you go to that course, this course is the same version, but using CUDA. Let me check how we are in the table. We have day 3, a break. So for the rest of the day, we will have we will play with exercises, and we will also do this. Or in case that you have finished our exercises and you want to play with this, we will use you can play with the conjugate gradient solver. That the algorithm is here on the wiki page. Okay, I'm checking I see on the wiki page is written in Julia, but I imagine that also if you do a search in Google, you could find the solution using C++ or C. So this will be the algorithm. Actually, it's in Julia, but it's kind of readable what it means to do. This is in case that you have time and you want to. But I imagine that have now plenty of exercises on this lesson. Okay, so now is exercise time. Let me check again what time is it? It's 20 past. So we will have afternoon break after 2, but I'll be around today until 4 p.m. One thing that I would like to share with you. Here, if we move to the Archer2 website, I will copy that in the chat. If you go to GPU programming with the HEAP, the sessions, the recordings are here. I've uploaded to YouTube, and the course feedback is. I know that actually, there is a term now that is called feedback fatigue. That is now everything that you do, you get a feedback form to fill in. All of the questions are optional, but the most important one, well, which course have you attended, and the overall satisfaction. This is the only question that is mandatory. So it goes from excellent, very good, good, bad, or very bad. Also, we said that if you have what you like most about the course, list, comments, and also courses that you will be interested in the future. There are other questions, but feel free to fill them or ignore them. The most important one is the overall satisfaction. If also if you have a bit of more of time, these ones. We need to report this feedback results to the UKRI that are, you may know, the course is free, but it's funded by UKRI. So we need to give good good number of feedback forms. So please, if you have the time to do so, I will share here in the chat the feedback form. Thanks again. I'll stop sharing. I will share I see there is a question in the chat. I will have a look right now. So the idea now is to do the exercises, and also if you have any questions. So I remember last week you wanted to comment something about the specific code. Please let me know. Before going to the break that is at 2 p.m., I would like to show you the architecture of I was mentioning before, we have talked about the Grace Hopper, that this is a NVIDIA, that will be something similar to this. But when we talk about the AMD, the MI300, we have different architecture. You see that here we have this will be the CPU, this will be the GPU. Know that because normally the CPU cores are bigger and have more features. GPU cores we have more that are smaller and less features, but let's see, for the GPU programming paradigm, we don't need as many features as the CPU cores have. And this is, let's see, a real unified memory. You see that the memory is the same for CPU and GPU. That this is like a different case that I've seen like I've been talking about the Grace Hopper, but I think there is now a new architecture that is Grace, and but this is like on Archer 2, the one that we have is similar to this. We have the MI 210. There is but entries close, the call for applications close today. In case that you're interested, there is a AMD GPU hackathon. That this is a collaboration between Archer 2 EPCC and AMD. The AMD experts will come to Edinburgh, and this will be a 3-day event. In case that you have a code that you want to port to GPU, or you have a GPU code that you want to improve the performance, you can attend. You just needed to fill in the application form. If you go to the here and you go here, you need to apply using this form. This you need to play as a team. Teams are between 2 and 5 or 6 members, and yeah, it's just sharing the name, email address, the members of your team, what the application is about, and the goals that you hope to achieve by the end of the hackathon. And with that, you will get access to the MI300. That is once they have a unified memory. So let me see. Yeah, I think we are now. Well, soon will be in afternoon break, and later, yeah, we will have exercises. And also, in case that you have any questions, or please feel free to. But regarding, let's say, theory content, this is let's say the end of the theory. Later, after at 2:15 will be questions that you may have with exercises or any other questions. So please feel free to stay and keep playing with the exercises of if you need to leave for some reason, it's not a problem. Well, before going on break, so thank you for attending these 3 days, and please keep in touch. Any questions? I will keep an eye on on Etherpad, but also feel free to send me an email, or also feel free to get in touch with James as well, that was the other course instructor. Well, have a nice break, and I'll be here until 4 p.m. If you have any questions or you want to chat, I'll be around.